ISGAN is the short name for the International Smart Grid Action Network, that is a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN creates a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids around the world. ISGAN consists of 27 contracting parties. Their nominated representatives form the executive committee, headed by 2 presidiums, that is assisted by 2 co-secretariats and the ISGAN operating agents. The ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through voluntary participation by governments in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, users and consumer engagement. ISGAN facilitates dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracted parties. The ISGAN value proposition relies on conferences and workshops, policy and technology briefs, discussion and technical papers, casebooks, and webinars. Within ISGAN, virtual learning offers the ISGAN community means of rational and continuous technical skills complement and update in the field of smart grids. The Academy is proposed as a set of e-learning and reading core modules dealing with the entire value chain of smart grids. The webinar of today concerns the demonstration of grid forming capabilities and synchronization services. This webinar focused 2 demonstration activities of the OSMOSE project on inverters interfacing energy storage systems that can be turned into grid forming units by using suitable control upgrades. This is achieved thanks to the provision of synchronization services to provide support to the power system when it hosts massive amount of inverter-based renewable stochastic generation. The speakers are Carmen Cardozo from RTE, Mario Paolone from EPFL, and Markel Zubiaga from Ingeteam. Please pose questions using the question and answer tool. The speaker will answer at the end of the presentation. The recording of this webinar will be available through the ISGAN YouTube channel. Now I leave the floor to the speakers. Please enjoy the webinar and the roundtable.
So hello everyone, I'm Carmen Cardozo. I hope you can see my screen now. So I will start this presentation with a bit of an introduction of our OSMOSE Work Package 3 project and the demonstrators. And then I will share the screen with Markel from Ingeteam, where we will share some experience on our specific demonstrator that we call RTE Ingeteam demo. I will speak about the specification of the grid forming capability, and then I will leave the screen to Markel to tell us a bit of the converter control design that they propose to achieve this performance, and then how we together develop compliance verification procedures. And in the second part of the presentation, I will leave the floor to Mario from EPFL with the second part of the presentation. So first, a bit of context. So what is this grid forming technology about? Actually, we have inverter-based resources that are currently connected to the grid. They are called grid following because what they do is that they measure the frequency from the grid that is today provided by synchronous machines. And then based on this measurement, they inject active and reactive power, basically current. And it was already shown in a previous project, Migrate project, that we cannot do this to high penetration of inverter-based resources. And another way to tackle the question was to ask ourselves if we can operate a 100% inverter-based resources system. This is the green line that we see on the top. And the question was, yes, if we redefine system needs, and the one way of achieving it was proposed by grid forming controls. And since the end of this project in 2018, we have many more control types, somehow control implementation in the literature, and even 2 high-power demonstrations that we can find reference in the literature. Moreover, in the beginning of this year, Great Britain published a code for grid code for minimum specification of grid forming capability. So during this process, actually, when we started this project, we realized that we needed to progress on the common understanding by the different stakeholders on the definition of this grid forming capability that seems so promising, but we have maybe different views on it. And in this framework, the objective of the work package 3 of the OSMOSE project was to demonstrate that this technical capability could be achieved with commercially available power electronic interface resources, more specifically energy storage systems. And a big question was if this solution can be scalable and economically viable by using off-the-shelf converters without oversizing them. And finally, a big question also is how to characterize the contribution of this technology to the system stability using external measurement and not only by knowing the specific implementation of the concept. So to answer this question, what we proposed in the project was to deploy 2 demonstrators. On one side, we work with Ingeteam in the deployment of a hybrid energy storage system, including 1 MVA of ultra caps, and then some 500 kilowatts, so 60 minutes of battery. And at the EPFL side, you will see that they work on an existing battery, a bit of the same scale. This case only lithium titanate battery. And the details of the specification of the demonstrator are published in one deliverable. Today, I will focus more in an overview of the contribution that we achieved within this project, thanks to the collaboration with these 3 entities. So with Ingeteam, we work basically in a first stage on the specification of what is this grid forming capability. Then, as I said, there was a control development part, not only on the grid forming AC-DC converter, but also on how to handle the DC power sharing on the DC side when we are in a hybrid setting. And of course, as I said, it was really important to test the performance of this device when submitted to disturbance of the grid like faults. And at EPFL side, they have a different setting. This time, as I said, a battery system, and that without access to the internal control. So in this time, we need to control the converters to get the expected performance by acting on the reference. And they work basically on this multi-service optimization approach. They also work in the performance assessment from the assessed grid measurements. All the deliverables below can provide more details on this research. And now I would like to focus on this first part of the presentation on the contribution that we bring with Ingeteam while working in RTE. So this is quite a technical part, so I will try to stay in a clear way for everyone. So basically the challenge, as I said, is defining what is grid forming capability that is suited for an industrial environment, that we can, TSOs can get the performance they're expecting, and at the same time, manufacturers are able to develop technological solutions. And in this work, we propose this definition that a grid forming unit shall, within its rated power and current, be capable of self-synchronized, standalone, and provide synchronization services. So to try to put it in more comprehensible words, what this means is that by definition, a grid forming unit does not rely on specific conditions to synchronize. So it can operate on a wide range of short circuit ratios and inertial level. That are the challenges that a grid following unit is facing today. Then we have this definition of synchronization services that actually include a notion of a natural, inherent, immediate, or undelayed deployment of synchronizing power, system strength, fault current, and inertial response. Again, this is the main specificity of a grid forming unit and what a grid following unit cannot perform. As it is based on the measurement, it cannot provide this immediate response that if we get a bit into the stability of a system, we will realize that is quite important. So basically, by providing these services, the grid forming unit can help others device connected to the grid to maintain synchronism under stressful conditions, while still complying with the general requirements applying to the technology. And the more important things that we can keep in mind from these results is that there is no overload or capacity reservation associated to the definition of the grid forming capability that usually entails a cost on the manufacturer. Then we do not expect any provision of traditional ancillary services like a voltage, primary voltage or frequency regulation associated to the grid forming capability. These are different services and a unit can choose or be mandated to provide independently of the synchronization mechanism. So the idea is to fill this gap that we have today in the definition of services that we have in what happens when you have this disturbance between 0 and the time that some units start providing services that exist today or will soon exist, like as frequency response, frequency containment reserve, frequency restoration reserve, or replacement reserve. So these are the three layers are ancillary services that are well defined today. Fast frequency response are ancillary services, deployed in some countries and to come, but what we propose is to have the synchronization services, and is the one are missing to cope with the first instance of a transient response. And today, where we can fit these synchronization services in our industrial framework, actually we have what we call non-ancillary, no-frequency ancillary services that have included until today steady-state voltage control, for instance, and some other capabilities that are requested to operate a resilient system like Black Star or Island operation. And we have been speaking now since a while of this inertia for local grid stability. And actually is there when we need to fit these synchronization services, because there is not only this local inertia concept that is needed to maintain stability on a local scale system dominated by power electronics. And what we'd like to highlight here is that there is a difference between these services. We cannot treat them as they are one only family, because we need to separate the requirements that apply in a steady state, the ones that are quite fast, but still leave room to measurements like the stability services, but then synchronization services need to be activated immediately and have quite low sustained time. So based on this definition, if we want to apply this definition on specific technologies like a wind farm, a storage system, a synchronous machine, or even a PV plant, they have different nature regarding the DC side energy that they dispose. So to cope with this difficulty, we can define types of grid forming units. So basically a type 1 grid forming unit has really low energy requirements. And we can go up like that, and a type 3 grid forming unit, for instance, is what we are doing today. It's energy storage system that have can provide inertial response, synchronizing power, but not necessarily frequency regulation, normal classical frequency regulation. This is an option, and it will be decided by the operator of the system, the battery system, I mean. And of course, to avoid any doubt, type 4 grid forming unit is a synchronous machine, and the specificity is that it can provide also high fault current. Other types, we will say that the fault current is limited to the rating of the converter. So how we demonstrate that we can achieve this type 3 grid forming capability with off-the-shelf equipment available today in the market? Well, we deploy this demonstrator with Ingeteam. So we have these batteries, ultracapacitor, then 3 DC-DC converter to manage this hybrid system. Then this AC and 1 MVA AC-DC grid forming converter. In this container, we have also a transformer and a medium voltage switchgear cubicle to connect to a 20 kilovolts bus bar. And this is what it looks like to have in this system. So this is the upper storage container, and this is the converter side, the transformer, and the switchgear that are in the lower container to connect to the 20 kilovolt bus bar. We must say that this demonstrator could not be operated with it connected at the end because we have an incident in the commissioning that prevents the continuous operation within the time frame of the project. However, we did perform some interesting effect acceptances that I will let Markel to present that allow us to affirm that we have these contributions today in terms of control design. So for the grid forming control, we work in two new things. That was the inclusion of a negative second component to the threshold virtual impedance current limitation strategy to improve the grid forming robustness to asymmetrical faults. In fact, if you have heard about grid forming, you will know that the challenge, one of the main challenges of this type of control is that converters are quite sensitive to high currents and they need to be protected. One technique is using this threshold virtual impedance, and there was, at the moment of the project, low research on the behavior on asymmetrical faults, and that was some contribution that Ingeteam proposed. And also we work a lot on the decoupling, as I said, of these synchronization services that for us is inertia from the frequency-related services that are those that can rely on the measurement of the frequency, like frequency response or frequency containment reset. And this can be achieved not only at the AC-DC converter level, but also at the DC device level. We can have power sharing strategies that decouple the balancing services from the synchronization one, such that the battery will do the balancing services and the synchronization services are handled by the ultracap. So now I leave the floor to Markel to tell us more about we can achieve this performance.
Thank you, Carmen. As Carmen told us, there was really little research regarding the negative sequence and how to handle the negative sequence with the grid forming control. So as always, control changes is mostly an evolution. So the first, we looked at the TBI. We watched that the activation of the TBI was used by the model of the current. And of course, when the negative sequence fault occurs, or with a fault with an inverted sequence voltage occurs, the negative sequence current flows. And that negative sequence current is seen at the model of the current as a 100 Hz oscillation. So this oscillation generated a triggering, a 100 Hz triggering of the virtual impedance, and the impedance behaves as a nonlinear impedance, like the starts and offs. And even if it's true that this protects the converter or the system or getting currents higher than the nominal, that nonlinear impedance, of course, it's a liability. So next, please. Okay, so based on previous experience on grid following, we took some control subsystem that consists on the estimation of the peak current. So when we have a current with components in positive and negative sequence, we can estimate the maximum current. So thus this current is continuous, and the triggering of the virtual impedance, it's linear, and we didn't know, or we didn't see any harmonics or any undesirable behavior. So from this point, that once we have protected and relatively good results, we started thinking that maybe we can also shape the behavior of the fault. Next, please. So based on that, we thought how we could add, or how the grid forming control can help in the grid during these events. So we proposed an additional impedance that is also triggered, but this time with the negative sequence. And this time, and this way, we can more or less, with its limitation, direct our nominal current or a variable current to the positive sequence or the negative sequence in order to help the grid by working in two different axes depending on this parameterization, by compensating the negative sequence or by supporting the grid voltage. So next, please. So the next, let's say that the next control algorithm that we worked on was the coupling of the different services, like the balancing related and the synchronization. So This we are seeing here the structure of the drup control. It's a PF drup control. That this control inherently gives inertia and inherently performs also the frequency related control, as this has a PF status. Next. So we added a filtering or a feedback from the internal frequency to the set point. So this way we can call transient grid forming or transient PF drup control. This way, if a change happens in the angle of the frequency, this still reacts the same way as the PF does. But if this change or the frequency change is extended in the time, the filtering prevents this control to keep acting. So in short, this avoids the frequency control by avoiding it, by decoupling it, and it still keeps the synchronization service. Of course, it's not for free. I mean, the inertia constant is affected by the filtering constant. So both have to be in accordance. And well, related to the frequency control also, let's say more or less that after two filtering constant, we can assume that the grid frequency is practically the same. So this way we achieved the coupling of these two services. So next, please. And regarding the last control improvement, we worked on the coupling the energy intensive and the power intensive services. To do so, a microgrid was created in the DC side. So inside the converter, as Carmen pointed out, we have 3 DC-DC converters. So these 3 DC-DC converters are regulating the bus voltage together. So by control settings, we can make that some of them, especially the ones related for some energy storage devices, in this case, the ones that are related to the ultra caps, they have really fast response to any change in the DC bus voltage. So these settings allows to, when the AC side demands a fast, huge active power demand, the ultra caps react fastly and gives the peak, while in the long term, as they have as they don't control with an integral component, in the long term, after few, let's say, milliseconds, and the battery takes up and gives all the active power. So next, please. So going more into detail about how we did create or set this microgrid, the DC converters, as they are related to the ultra capacitors, have a proportional gain, while the battery related DC-DC converters have a PI with a strong integral component and really a low proportional component. So with this fast DC control for the ultra caps and slow but accurate with the batteries, we achieve the decided decoupling by allowing the ultra caps by reacting fast and allowing the battery to react slowly, but in the long term. So now I will give the word to Mario to continue. Okay, no, is the okay?
Sorry, Markel.
Sorry. Yes. Sorry. Okay. This is the setup in the laboratory. Here we are, Carmen and me, and this is well, this is more. It's not about the technical slide, but this is interesting to see how we tested and we improved the control algorithm. Here is the PCS, the converter. Here we have the AC-DC converter and the 3 DC-DC converters. We also used a resource from our lab to use a converter, a back-to-back converter as a virtual grid. And we also moved some battery racks and ultra-cap racks in order to have the same setup as we had in the containerized solution, but in our laboratory. So with the real equipment, but without the container, of course, we did some fat tests, and that's how we developed our control and achieved our results. And this is the results, the fat results. Here, this is the answer of the converter regarding the synchronization power. But the synchronization power, we did the test with a angle change on the grid. So when the grid changes its angle, the grid forming control reacts by smoothing the frequency and giving this power. The next results are related to the inertial response and the answer regarding the rock-off. Here, we can see that there are different setups regarding the transient grid forming. So the inertial response, the first surge or the first peak, it's really similar, and it's more related to the inertia, while the duration of the injected active power is more related to the transient grid forming settings or transient grid forming filtering constant. And lastly, we have here some results regarding the unbalanced faults. Here also we have some results with two different settings. And one is the upper side is the voltage, and we can see the blue one is the positive sequence voltage, and the red one is the negative sequence voltage. So depending of the settings and depending on the current in the low side, you can see that depending on how much current you redirect to the active to the positive sequence or the negative sequence, the voltage is supported in a bigger degree, or the imbalance is compensated in a bigger degree. So now, yes, I give the word to Mario. Okay, so Mario, keep on.
Thank you, Markel. Can you stop sharing your screen, please? Thank you. I hope you can see my screen, and I will continue this presentation by illustrating the activities that have been carried out at the EPFL in Lausanne within the context of the OSMOSE project. So here are the 4 bullets I'm going to discuss. The first one is the description of the control framework, the experimental setup, performance assessment, and then the extension of the control framework that we proposed to a simulated system, whereas the first part of my talk will be purely devoted to experimental activities. So the motivation is the same that was introduced by Carmen. Essentially, we wanted to study the provision of inertial response and frequency containment from battery energy storage systems, since these devices are advocated to be a potential remedy for frequency regulation of grids that are hosting a substantial amount of distributed generation with converted interphased supply. Why we are talking about multi-service systems? Well, the simple reason is here because the amount of regulation services, frequency containment, frequency restoration, and frequency replacement reserve, is tightly coupled with the errors that are injected into the system due to forecasting errors of both renewables production loads, fast variations of renewables, as well as classical power plant outages. Therefore, the natural service that you can couple together with the provision of the frequency control reserve is dispatching. So essentially, if you have a perfectly dispatchable system, ideally speaking, you don't need any reserve, right? Therefore, one of the natural questions that you may ask yourself, if you own a battery, is can I use the battery to dispatch my local grid and layer the battery capacity to provide also frequency regulation? Because first of all, in this, with this double usage, you compress the amount of reserve and you provide reserve to the system. And from the owner's perspective of the battery, you also maximize the value of the battery in terms of absorptions of the investment cost of this asset. And the question for us was, okay, how do we formulate this multiple service provision from the control design? And this is what I'm going to talk about. So, as I said, the objectives of the control framework that we developed is to achieve the dispatchability of a local medium voltage system. In our case, was one of the feeders of the EPFL campus, which is hosting a substantial amount of stochastic, so non-controllable distributed generation and loads, and at the same time provide frequency containment reserve to the main grid, as well as voltage control to the local grid. Since your battery converter can work on 4 quadrants, you can use also this feature to provide reactive support to the local grid. So in our framework, the only controllable elements is the battery or the batteries. If you have a fleet of them, I'm going to discuss the results only for one, but the same results can be extended to a fleet of batteries. Now, from the design perspective of the control framework, you have mainly 3 stages of the control. The first one is a day ahead stage. Let me use the laser pointer. So in the day ahead stage, what you have to essentially quantify are what we call energy and power budgets that you essentially allocate for each generic service J that you see here. So in our case, we have 2 services. You can have also more than 2. So you have a budget which is allocated for the dispatching and another budget which is allocated to the frequency control. And your problem is essentially to allocate these 2 budgets such that you're providing both services at the same time. So the output variables, the decision variables of this control stage are essentially the droops for frequency and voltage, as well as GN hat. So what is the GN hat? So essentially your dispatch plan, okay? Then you enter into the intraday operation, which is a dispatch tracking problem together with the provision of the frequency control. And this is typically a problem that is an intraday problem with a slice, with a time horizon, which is correspondence of the sampling that you have adopted for your dispatching. It can be 1 hour, can be 15 minutes, can be 5 minutes. This depends on the user. And essentially your control objective is to dispatch your system within these 15 minutes, 1 hour time horizon, and at the same time provide your frequency control. Then you have a third layer, which is the hard real-time layer. What is this third layer? Well, essentially is a sort of certificate of compliance of delivering the services. What I mean with that, you see this graph that you have on the slide. So this graph essentially represents the capability curves of your converters on the PQ plane. You can see that these capability curves are multiple. Why? Because essentially these curves are dependent on the AC and DC voltages on the converter sides. Therefore, what you want to do is to guarantee that any set point that is issued by the dispatch tracking, let's say the intraday problem, is compatible with these capability curves. And we have developed a framework which is capable to ensure that this compatibility is satisfied. Okay, so essentially you guarantee that what you promised in terms of regulation services is actually satisfied by these dynamic capability curves of your converter. So they're like a sponge because they depend on your decisions, on your decision variables, as well as also stochastic variables like the voltage that you have outside the system, which is also fluctuating because you cannot control the slack voltage entirely from your controllable asset. Now let's dive into each one of these layers. So in the day ahead stage, what we do is that we are adopting forecasts of load and PV production that we denote with the letter L. These are completely stochastic in the sense that they are forecasted and are not controllable. So we suppose that there is no demand side management, there is no control on the PV or wind production. They are completely uncontrollable resources. Then the purpose is to compute a dispatch plan, what I told you before, so the G hat, by estimating the amount of energy, of course, power, the energy just the integral of the power, that I denote with the letter F, that is required by the battery to track the dispatch plan for all the possible scenarios. What I mean with that? Well, I mean that integrated into your dispatch, into your G hat, you have what we call an offset profile, F. So this offset is essentially responsible of keeping the battery state of energy, or state of charge if you want, to a level such that for all the possible realizations of the scenario that you simulated, the battery is always capable to compensate for the errors. So it's a robust optimization framework that we developed to satisfy this need. Okay. Then if at the end of the day ahead dispatching exercise, you have enough capacity of the battery that is not used, and this you can compute day ahead because you do this computation for all the possible scenarios, the leftover capacity of the battery is used to compute the maximum droop coefficient that your battery can provide to the system. Okay, this is how we prioritize the services. We first do the dispatch, and then with the leftover capacity, we allocate it for a given droop, so regulating energy to the system. You can also invert them. It's up to the user to invert these two services. But we prefer to have this hierarchy with the dispatching first. Then, as I said, there is a dispatch tracking. This is realized by a model predictive control algorithm, which is acting in this intraday time horizon. As I said, this depends on the granularity of your dispatching plan. It can be 1 hour, 30 minutes, or 15 minutes. In our case, it was 5 minutes. And this MPC is using short-term predictions of the aggregated feeder presumption, so essentially load and photovoltaics. And he's also using the battery circuit model, in our case, with a TTC model, to forecast, let's say, to simulate the battery DC voltage, which is then used also for the capability curve computation. Okay. So the interesting aspect of this MPC is that he's using information, let's say forecast, short-term, that were not available in the day ahead. Okay, because essentially you're using information which are just before collected, just before the time horizon where you are acting with the MPC. And of course, these forecasts are way more reliable what you did the day before. Of course, you have a constraint of satisfying the tracking that you promised in the day ahead. Then you have the real time. As I said, the real time control stage is essentially is taking into account the battery state of charge, the AC grid voltage, the voltage of the DC bus, thanks to the battery model, the active and reactive power capability curves. And essentially, by solving an online optimization problem, is capable to satisfy that the set points which are issued are compliant with the capability curves that, as I said, they move, they are changing according to the AC and DC voltages. So essentially what we do is that we embed the dynamics of the DC and AC bus voltages into the optimization problem, such that we guarantee that we are always inside the capability curves due to the actions of the converter, because these voltages, of course, depends on the power flows on the DC and AC buses. Now, let me describe the experimental setup. So on the figure on the right, you see one of the feeders where we're carrying out the experimental activities. Is one of the feeders of the EPFL campus. You can clearly see the photovoltaic panels. And in this video that you should see on your screen, you have an aerial view where you can see the locations of the buildings. So the ELL, ELH, ELE, ELG buildings, and the location of the battery that was a controllable element of our device. The feeder is connected to a sub-transmission grid with a rated voltage of 50 kilovolts. Is the substation called Franklin. That is our, let's say, point of common coupling with the upstream grid. So here you can see the video with this is the laboratory on the left. You see the battery. So this is the battery that was our controllable device. As Carmen said, electrochemistry of this battery is lithium titanate oxide. Rated power was close to 1 megawatt, and rated energy was 560 kilowatt hours. So this is a summary of the main characteristics of the feeder. So the base load is 140 kilowatts. We are hosting on this feeder a little bit more than 100 kilowatt peak of distributed PV generation. As I said, load and PV are uncontrollable. And we equipped this feeder with a phasor measurement unit infrastructure. And we use it, we have PMUs in all the buildings, but the PMUs that we use are located here on the low voltage side of the battery. So essentially on the AC terminals of the converter, and in correspondence of the point of common coupling with external grid. So these are the two PMUs that I'm referring to in what follows. So these PMUs have been developed by my laboratory. They are compliant with the IEEE C37118 standard. They have a reporting rate that in this experiment was 20 milliseconds. But the very peculiar characteristic is that their accuracy, certified in our laboratory, is of 1 millideg, so in the range of 18 microradians. And the reason why we were interested to that value is because we wanted to measure very low values of ROCOF, of rate of change of frequencies, by looking at the angle opening of the voltage phasors between these two measurement points. And of course, since we are in a distribution system, these angles are very tiny, and we need a device which is capable to do such a measurement. So let's look at the performance assessment of the grid forming versus grid following units in our demonstrator. So this is a visualization of a day of operation. So on the top right figure, you see the scenarios which are generated thanks to forecast in day ahead. Okay, you can clearly see in the middle of the day the presence of the PV, since your load is experiencing a sort of sink due to the injections of the PVs. Now, you can see also the spread of the scenarios, which is essentially giving you the uncertainties, the superposed uncertainties of your load and PV generation. In the middle figure, you can see the power budgets that are allocated for the compensation of the PV uncertainties and to the load uncertainties. You can clearly see that in the middle of the day, you have the majority of the uncertainties coming from the PV generation. And essentially, if you realize the top profile that corresponds to the bottom scenario, or the lower profile of the PV that corresponds to the top scenario, essentially you end up into different trajectory of your state of charge of the battery. So let's suppose that your battery is starting at the beginning of the day with a given reference state of charge. If you integrate these uncertainties into your system, you know day ahead that at the end of the day, you're going to end up into a certain state of charge of your battery, meaning that there is a leftover capacity of your battery that can be used for primary frequency control. Okay, so this is how the framework works. We're able to compute the energy budget needed to compensate for these uncertainties for the dispatching, and the leftover energy budget is used for computing optimal droop that is allocated to the battery. So in this specific day of experiment, the droop that was allocated was of about 100 kilowatt per hertz, just to give you an idea, a number. So this is the result. So on the top right curve, you see in continuous black, the dispatch plan G hat that was computed day ahead. In dashed red, you can see the presumption, so the superposition of your generation and your load without the control of the battery. And you can clearly see that there is a mismatch between what you computed day ahead and what has been realized. So essentially, in the first half of the day, the forecasts were underestimating the load, and in the second part of the day, they were overestimating the load of the system, the aggregate load of the system. So clearly here, there was a negative and a positive error. Now, in color, you see the power of the battery, which is in red, used for the dispatching error compensation. You can clearly see here is negative and here is positive, according to the sign of this mismatch. And in light blue, you see the power, actually you see here, I hope you can see my laser pointer. This is the power that was given by the battery to provide a frequency control reserve, okay? If you superpose these two, so the red and the blue, together with the dashed red curve, you end up into the aggregated power consumption or production at the point of common coupling. And you can see that the black curve is practically superposed to the dashed gray area, which is eventually the PCC power. So actually, what this figure is telling you is that we are reliably dispatching our feeder and at the same time providing frequency control reserve. In the middle figure, you see the frequency of the system and essentially the action of the power injections. And in the bottom figure, you see the state of energy of the battery along the day of operation. You can clearly see that this was always within the bounds that are essentially binding constraints for the operation of the battery. So we can say that we reliably track the dispatch plan, and we also provide successfully frequency containment reserve. We have done days of experiments like this, and we also operated the system for multiple days in a row, and the results were according to what I'm showing you here. So now, how have we quantified the impact of controlling the battery as a grid forming or a grid following unit? So what we used as a metric is the relative rock-off or relative rate of change of frequency. What is the relative rock-off? Well, it's very simple. It's essentially the ratio between the rock-off, so the delta frequency at the PCC over time, divided by the amount of power that the battery is injecting to provide the primary frequency control. Okay, so essentially, if you want, is hertz per second per watt. Okay, so why we did that? Essentially because we wanted to express the impact of the regulating power with respect to the variation of the frequency over time. Okay, and we wanted to make it in per unit of the injected power. Why? Well, the reason is very simple. If you want to compare grid forming and grid following in an experiment, it's impossible to have the same frequency variations. So that's why you have to put it in per unit of the regulating power. In this case, you can run experiments in series where the frequency dynamics are not exactly the same, but you have a metric which is removing the fact that your frequency dynamics is not exactly the same. Okay, so essentially the metric is independent from the actual frequency variation, since the rock-off is divided by the VSS regulating power. Sorry if I'm being redundant, but that's a key concept. So here I'm showing you the cumulative distribution function of this relative rock-off. So on the horizontal axis, you have the hertz per second per watt, so the relative rock-off, and on the y-axis, you have the probability. You see 4 cases, okay? Case 1, 2, and 3 are for a grid forming control unit. Case 4 is for a grid following control unit, okay? So case 1, 2, and 3 are differentiated in the sense that the case 1 is referring to the CDF of the relative rock-off for an observation window of 24 hours, okay? The case 2 is the same control with a multi-service provision on the hourly transition. Why I'm focusing on the hourly transition? Well, if I go back, you see that in the hourly transition, as you know, we always have the largest frequency deviations. This is due to the imperfect market that we have at European level. That's a very well-known problem. So that's why we wanted to see whether the behavior of the converter was essentially independent of the frequency dynamics. And the case 3 is the grid forming units providing only the frequency control, the primary frequency control, and not the multi-service. And why we used case 3? Essentially because we wanted to be sure that the superposition of the dispatching was not disturbing the grid forming action with respect to the primary frequency control. And the reply was positive because you can see that these 3 curves are basically superposed. So what you can say is that the multi-service provision or the single provision of frequency control reserve are essentially decoupled from the frequency dynamics perspective with respect to this relative rock-off. Then we compare with the case 4, which is the grid following, providing only the frequency control. You can see that the CDF is way more spread, which is a bad news for the grid following controller, because essentially it is unable to keep the local system frequency is stiffer around the rated value. So essentially the frequency which is spreading around in the CDF is telling you that essentially the impact on the local grid frequency was stronger in the grid forming control unit. Then what we have done was an extension of this analysis to a whole system, because this analysis was carried out on the EPFL campus. So then you can ask yourself, okay, what if we extend this to a bulk system? So what we did was to take the IEEE 39 bus model, which is a pretty well-known standard. And what we did was to replace 4 generation units with 4 wind farms. So essentially we take the 4 biggest generation power plants in the model, and we replaced them with the 4 wind farms that are modeled in details. And we added a battery in one of the buses of the system that has a capacity and an energy very close to the battery that has been installed in Australia, for instance, for frequency control purposes. So each node of the system is equipped with a PMU, which is compliant with the CEST standard. Actually, this PMU is the same in terms of algorithm of the one we selected on the campus. So if you're interested, this model can be downloaded for free in a GitHub. And these are real-time simulation models written to be running on the Opal RTE simulation platform. The interesting thing is that the inertia constant of this reduced initial IEEE 39 bus system was, if I'm not mistaken, 60% lower of the original inertial constant of the system where they were the original synchronous machines. So we really curtailed by 2/3 of the inertial response of the system. So how we did that, the simulation, essentially, we had a 2-layer simulation. So we produced a day-ahead scheduler of the demand, and by using demand and wind generation forecast, we computed frequency containment restoration reserves according to the grid codes that are basically in agreement with the ENSOE practices, let's say in Europe, in continental European model. And for the instead of the market, we replaced the market with a unit commitment model. Okay. And then in the real-time layer, we had the hourly energy generation and reserve schedules generated by the day-ahead layer. And we produced the realistic demand and wind generation profiles according to the forecast that we're producing day-ahead. And then we compare the grid forming, grid following converters interfaces for the battery, and we compare them over a 24 hours long real-time simulation. The results are essentially the same what we obtained experimentally on the EPFL campus. You can see here we are comparing the CDF or the relative ROCOF. This is the average relative ROCOF in all the 19 nodes of the system of the grid forming, which is a continuous curve, versus grid following, which is a dashed curve. On the left is for a droop of the battery of 225 megawatts per hertz, and on the right for a PF droop of 450 megawatt per hertz. Again, the grid forming has a way stiffer CDF, meaning that is capable to maintain the ROCOF per regulating watt of power way closer to zero. So essentially capable to stiffen the system response. So conclusions, the research experimentally validated the grid forming control of battery energy storage systems, providing multiple services using a medium voltage or utility scale battery energy storage system that has been hosted on the EPFL medium voltage feeder. We have proposed metrics that have quantified the performance, the superior performance of grid forming controls compared to the grid following one. And we have also analyzed the scale up of this conclusion to the low inertia IEEE 39 bus benchmark network that again demonstrated the same conclusion regarding the grid forming control superiority with respect to the grid following in terms of improving the system frequency containment. So takeaways are essentially 3. We can consider grid forming battery energy storage systems as effective assets to provide inertia, frequency control reserve, as well as absorb stochastic aspects at the local distribution levels, which is always beneficial in terms of compressing at the bulk level the frequency containment reserves. So this contribution from batteries, from local batteries, may be certified by adequate grid codes and market mechanisms that at the moment are rather primitive, I would say. that have to take into account the peculiarity of this technology. And I think that there is a long path to achieve these results. The last takeaway is that they had an intraday dispatch of active distributed networks hosting both stochastic and controllable resources need to be also regulated in view of its large potential to reduce frequency containment and restoration of reserves at the bulk system level. At the moment, also, this aspect is, let's say, taken into account by aggregated dispatching, but still there is a long way to go to take better into account and valorize also this aspect at system level. With this, I finish my part of the presentation and I hand over to Carmen for the final remarks.
Well, I don't know. Yes. So I think that you have already kind of wrap up all this contribution, and I will just finish by saying that yes, on RTE side, thanks to this collaboration with Ingeteam and with EPFL, we do think that we have work to do on the specification of this grid farming capability on the grid code. I think that this experimental validation have already shown that we can achieve this performance without oversizing, while still providing traditional synchronized services, remaining robust to disturbance. And so it's exclusive. You can be grid forming and still, like a grid forming, choose to provide ancillary services or balancing services or other tracking or flexibility services and get the same performance and without degrading what is expected to do a grid forming. And then I think this definition of synchronization services will help us characterize this required performance from the system. And again, it's important achievement for us to succeed to decouple these services. And just to finish, yes, we need to keep working on the certification. So how can we certify and verify the compliance of this unit? There is a lot of work on progress, and that will continue. So I think that we maybe can answer some questions. I have been doing it in the chat. If you feel that the response does not satisfy you, you can launch another question, please.
Thank you, Carmen. Thank you, Mario, and thank you, Markel, for your presentation. Yes, now it's time to open the floor to some questions. So I saw that I mean, some questions have been already answered during the presentation. Thank you for that. And for now we have a question that is open, and I will pose you this question, so feel free to answer. It regards the time step that is used for real-time control. The audience asked, what is this time step that you are using for real-time control?
Okay, perhaps I can take this question. So regarding the real-time control of our last stage of the 3-layer control framework is 100 milliseconds. So if you're interested, we published a paper on the interoperability transaction smart grids where we show how to formulate and solve an approximated convex optimization problem, which is computationally efficient, because this part of real-time control is a constraint optimization problem, which is pretty tricky to be solved. So yeah, what we achieved was 100 milliseconds on a standard microcontroller. If you're interested, I can post on the chat response the reference to this paper where you can have all the details.
Thank you, Mario. Yes, actually, it will be nice to have some if you have some reference to share to the audience, we can include these links in the YouTube video, because we will share the recordings. Yeah.
Fantastic. I've just done it. I just posted the reference to the paper.
Thank you very much. We have 2 more questions. The first one, can you please comment on the use of frequency deadbands, which are usually implemented in virtual inertia control in the case of feed following sources? Will such a deadband be necessary for grid forming sources?
I can start maybe. Comment on, I think that what grid following sources do, I think there is big debate on that, but this is not inertia. Some people is calling this synthetic inertia. Actually, this is fast frequency response because we rely on measurement. And even for frequency response, I mean, from system operator view, we consider this kind of deadband undesirable. There are some, maybe, of course, then there has been some services that have been created with this deadband to have only like emergency action. Okay, why not? But for me, what is clear is if you rely on measurement, this is not inertial response. And if you should, for sure, in this application, do not consider this kind of deadband, and knowing a grid forming source, there is, I mean, we lost all the interest if we think of adding this kind of deadband. Mario, I don't know if you want to react.
Yeah, for this reply, I fully agree with you. I would not add anything else. Regarding the second question on the DI over DT, maybe Markel, since you have experience on the ramping rate, on the derivative rates of currents of converters, maybe you can take this. Markel, you're muted.
Okay, now regarding maybe the question 2, like I think that there is no derivative limit for the current. I mean, the grid forming control should be capable of limiting the current for a variety of short circuit ratios, and I think that they should work the same as the grid following. So in that terms, I think it will be the same. No limit in the derivative.
Okay, thank you. And well, there is a question regarding whether there are other webinars planned to present the OSMOSE results. Well, I can say from ISGAN side that we have other 2 webinars that will be held now in April. The first one will be the 7th of April. And the last one will be the 21st of April. I encourage you to visit the ISGAN website and register for these 2 webinars that will complement the overview of the OSMOSE results. I don't know if the speaker have other events regarding the OSMOSE dissemination.
Yes. Since we're at the ending of the project, we have several communication activities going on, but please just check the project website. We have been advertising all the other events from sharing the results of the project. Maybe one last thing, Mario, there was a question about the EPFL converter. I answered it because the question was if the Ingeteam converter was used in your, I say no, but I don't know if you want to maybe complete, because I just said there was different technology manufactured. I don't know if you want to complete the answer I provided. It was the second question that is in the resolve part. You are mute. I'm sorry, Mario, you're mute.
Thank you. Sorry. So the converter we use in our battery was not provided by Ingeteam, but was an on-the-shelf converter manufactured by a German company called Vagnoni. Now the company is no longer existing under this name, but they have changed the name. But it's a very standard on-the-shelf converter.
I see that we have a new question. To investigate
Yes, thank you.
the remuneration process of multiple cases, can we rely and get the value of the services? I think I will start because we have kind of a strong opinion on that. We have a starting point. And before talking about remuneration, we wanted to investigate cost, because I think that this cost has been used as kind of an authority argument or fear argument in the community not been really productive in the debate. So our hypothesis was what can we get for free? So can you develop a control using off-the-shelf equipment without any curtailment, without any oversizing, just by control, addition, modification? Of course, we are not getting our, what we call here, St. Nicholas Christmas gift. We're not getting all the services that we need to stabilize this system, but the question was addressed otherwise. If I just modify control, so this is no cost on hardware or operational costs, there are no costs, what can I get? And for us, we can get already a good thing for the system, for the sustainability of the renewable energy sources integration, without having any capital or operational cost. And this is what we have defined as minimal grid forming capabilities suited for grid connection requirements. And as I said, then on top of that, we might need capacity reservation. Then, of course, we might need a system to a mechanism to remunerate and to cover for this capacity reservation. But for what we did, no, for us, cost is zero.
And perhaps I can provide a complementary reply to you, Carmen. I mean, there are colleagues that are carrying research in various universities and also research centers where they're trying to forecast the prices for the imbalances that are translated into costs for dispatch tracking errors, and forecasting also costs for volumes of reserve to be scheduled and activated. Of course, even if you, I mean, in any case, you have to have this cost forecast day ahead that you can introduce into your scheduling of the multi-service provision in order to prioritize where the battery can be used in terms of capacity reservation. I'm sitting myself in the shoes of the owner of the battery, not in the shoes of the RTE. Okay, so that's why I'm replying complementary from what Carmen was saying. So there are people looking into it, and they're trying to correlate the cost of the dispatch errors and the cost of the scheduled activity reserves as a function of various parameters, but those that are looking more promising are essentially the uncertainties on the meteorological forecasts. In the regions of Europe, of course, where you have a substantial amount of renewables. If you have such a forecast methods, then you can play with them in order to schedule optimally your battery to maximize revenues. Of course, I'm sitting myself in the shoes of the battery owner, but yeah, that's possible.
I think it is not only complementary. I think it's even compatible, because for me, yes, you are if you are an operator of an asset, you maximize your revenue. And our point is, if we can only use for grid needs the non-allocated capacity that it's real time, it's 1 second left. So this capacity that did not find any value in the market, should not be withheld at the risk of putting the system in danger. It should be made available for system. I'm not asking you to reduce your optimization or multi-service optimization. You please optimize until even, I don't know, 5 minutes before all you want. Do whatever you need to do to make your money. But 1 second, when it left 1 second to real time, I don't see what it should be reasonable to withhold capability and let the system in danger.
Yep, absolutely.
Thank you for your answer. It seems that there are no more questions, so I leave you the floor in case you want to make some final remark before closing the webinar.
Well, I think that the project was extremely successful, specifically on that part. So I think that we contributed not only to the literature on the subject, but also to the technical understanding of the capabilities of these assets. And I truly believe that what we developed and in general what we contributed to can be one of the pathways to address one of the main concerns of the power systems operators regarding guaranteeing a sufficient amount of reserves at various timescales. And I do believe that what we produced was a valuable contribution to the technical literature and to the technical expertise.
So thank you. I just also learned a lot with this project. Thank you, the audience, for being there, for the question. And please do not hesitate to contact us. I think you will get the slide, you will get all the reference, the deliverables, and you have your emails. If you would like to continue discussing or you have further questions, do not hesitate to contact us, Markel or Mario or myself, please. Thank you.
Thank you. Have a nice day.
Thank you.
Thank you, Mario. Thank you, Carmen, and thank you, Markel, for your outstanding presentation from ISGAN side. We have been glad to host this webinar, and I remember to the audience that 2 more webinars regarding the OSMOSE project are planned in this month. Please check the ISGAN website, and please look for the recording of this webinar to the ISGAN YouTube channel. Thank you for joining this webinar. Have a nice day.